Okay, well, let's go ahead and get started. Welcome back from the break. We still have folks coming in from the dining area, but we need to stick to our schedule. So welcome back. And on behalf of the Planning Committee, I'm Steve Arnold. I'm the Deputy Executive for Space Formulation at Johns Hopkins APL. And I had the honor of co-chairing this symposium along with Michelle Thaler from NASA Goddard. And just wanted to give a big thank you to everyone that showed up this year. Attendance numbers are healthy. Feels like we're back from COVID. Overflow seating, it's been really great. And so thanks to everyone. It was great to see Mackenzie here as well each and every day. So well done. But let's go ahead and continue on with our program. And we have a special delivery for you now, the discussion of the future of sample return. And as we kind of constructed this panel, this one garnered a lot of excitement. You know, as we talk about as a community going and visiting places, I mean, the ultimate goal is to bring back samples, right? And so very exciting times, and we're living in it right now. So to help lead us into our final panel here, we have Pete Andreessen, who is our moderator for the session. Dr. Andreessen is the navigation team chief for the OSIRIS-REx project. He works for Kinetics. And throughout his 30-year career, Pete was fortunate to have explored asteroids, planets, moons of the solar system as a key navigation team member of several of NASA's deep space mission. Leveraging over 3 decades of excellence in aerospace engineering, Dr. Andreessen has earned distinction as an expert in orbital determination. Welcome, Pete, and please kick us off.
Thank you. Welcome to this special delivery of the future of sample return. This panel will, building on the success of the NASA OSIRIS-REx sample return from asteroid Bennu and reflecting on the challenges with the Mars sample return. We also consider plans for the lunar sample return mission. The OSIRIS-REx program's sample return success is attributed to engineering, science, and management with emphasis on rehearsal of critical events, and then advances in lunar sample return planning and are being coordinated via the Artemis program. With that, I'll introduce our panel. We have Rich Burns, who serves as the project manager for the space science mission operations at Goddard Space Flight Center. In that capacity, Rich served as the project manager for OSIRIS-REx during its operational phase. Rich hails from Adirondack Mountains in New York. He earned his mechanical engineering degrees from Notre Dame and Stanford. Rich has worked at Goddard Space Flight Center since 2001, since transitioning from 10 years of service at the Air Force Research Laboratory. Then we have Dr. Daniel Glavin, who's an astrobiologist. He looks for the chemical building blocks in the meteorites, asteroids, comets, and other extraterrestrial samples. He earned his BS in physics from the University of California in San Diego in 1996, and a PhD in earth sciences from the Scripps Institute of Oceanography in 2001. Excuse me. In 2004, Dr. Glavin joined NASA's Goddard Space Flight Center to continue his astrobiology research and help with the chemical engineering or chemical experiment on the sample analysis at Mars, this instrument on the Curiosity rover that is searching for organics and other biosignatures on Mars. In 2014, he became NASA Goddard's Associate Director of Science in the Solar System Exploration Division, and currently is the senior scientist for the sample return at Goddard. Dr. Glavin is also a co-investigator of the OSIRIS-REx sample return mission and is leading the organics in the organics analysis team. And then we have Dr. Dana Hurley, who is sitting in for Dr. Brett Denebe, or Denebe, who is the PI on the Artemis 3 geology team for the lunar sample return. So Dr. Dana Hurley studies the evolution of volatiles in the inner solar system and the effects of space environment on planetary bodies. She is a member of the Artemis 3 geology team, where she will focus on developing science objectives and a sampling strategy for system exploration research, my eyes are getting for understanding lunar volatiles. Dr. Hurley is also the PI of a NASA Solar System Exploration Research Virtual Institute team, focusing on laying the science foundation for future lunar exploration in the field of evolution of volatiles in lunar polar regions, solar system chronography, and cryogenic sample handling. She is also the supervisor of the Space Science and Instrumentation branch at the Johns Hopkins Applied Physics Lab. With that, let's see, first we'll have Rich Burns go over give an overview of the OSIRIS-REx mission. I will then cover the navigation of the OREX spacecraft back to Earth for Earth return after collecting sample from the small asteroid Bennu. Danny will discuss the analysis of these asteroid samples and review the science that will be enabled by the Mars sample return mission. Dana will discuss the plans and science for the Artemis 3 lunar sample return mission. With that, Rich, go ahead.
Thanks, Pete. It's my great pleasure to be here. Tell you a little bit about our journey to Bennu and back, and particularly with some focus on the challenges we encountered, mainly from our asteroid. Wanted to start with the happy ending at the end of the story. My father, took up reading in his retirement, and he wouldn't read a book that wasn't guaranteed to have a happy ending. So I wanted to make sure everybody was clear. Things worked out at the end. Don't worry if there's doom and gloom along the way. Here's what we knew about Bennu before we launched, right? We knew the orbit very well, of course, and there was radar observations from the ground, from Arecibo in particular, right? And which had a shape model which proved to be pretty much correct down to its level of granularity. There was also thermal measurements of properties of measurements of the thermal properties of the asteroid that suggested that it would contain large areas of fine-grained material. So our sample collection mechanism was designed to pick up fine-grained material. What do I mean by that? Things less than 2 centimeters in dimension is effectively what it meant. Here's what we found. Once we spent 2 years getting to Bennu. Once we got into orbit around Bennu and began taking images, we found that Bennu was an active asteroid. It's a surprise to everybody. You can imagine you're a couple kilometers away from the surface, and all of a sudden you see your target is shooting stuff at you. It's a little unnerving. And we were unnerved, I will say that. But quickly we looked closely, and we have an excellent navigation team, as Pete will tell you about it. And we very quickly came to the realization that, yeah, there were things coming off the surface of the asteroid, and that was great science. I should point that out immediately. But we were most concerned about the safety of the spacecraft and whether it was safe to remain in orbit in such a unexpectedly dynamic environment. Our team quickly got to work analyzing the trajectories of the particles and their mass, their size, energy, effectively, is what we were worried about, right? Because potential collisions with the spacecraft, obviously, we're concerned that we could either contaminate our spacecraft, optical surfaces in particular, or cause direct damage. And what we determined was the fluence of these particles and their energy was highly unlikely to damage the spacecraft. So we ultimately remained in orbit, but it was a few weeks of unexpected excitement immediately after we had entered orbit, which I don't say came came immediately or inside of a regional commercial network outage. So the maneuver to enter orbit was in the presence of a network outage at our main operations center. Oh, and there was a blizzard too. So that made things a little spicy. Okay, so we're in orbit around Bennu, and we always, I think somebody mentioned earlier, anthropomorphizing their spacecraft. So when I say we, I mean the spacecraft, but we feel integrated into the spacecraft. So we got to Bennu. We immediately realized the thermal properties of the spacecraft may have been measured from Earth, but they didn't really mean that there was large areas of fine-grained material. There's huge boulders littered all over the surface of Bennu. We spent a couple, 18 to 24 months mapping the surface, and it's really a rubble pile asteroid full of large boulders and challenging topography. Our spacecraft was designed to deliver the TAGSAM had our collection mechanism to touch the asteroid within 50 meters of a specified location, and in an area that contained lots of fine-grained material, free of hazards. In other words, areas where the spacecraft couldn't tip over if there was a discontinuity in the slope. There's nothing like that on the surface of Bennu, so we had to make lemonade out of the lemons. All right, our asteroid was not conforming to our preconceived notions of what it looked like, so we had to make the spacecraft dance, and we did. We originally I mentioned the 50-meter requirement, but we could only find areas on the asteroid that were on the order of 8 meters in diameter. So we've already got a reduction in our deliverability, allowed deliverability area. And even then, right, there were this analog we drew to delivering the spacecraft to a parking lot size area. We still had cars in that parking lot that we had to avoid. In other words, there's big features in there where we said, hey, we can't touch that area, or the spacecraft may tip over, or we may back into a large feature on the asteroid. So obviously we didn't want that to happen. How do we handle that challenge? Back in the critical design review phase, I should start with saying the primary sensor intended to get the spacecraft to the surface was a LiDAR, so measuring directly range to the surface. In the critical design review phase, a secondary capability using optical navigation was added to the spacecraft as a backup, and we utilized that capability because the LiDAR, the surface was just too discontinuous to manage. We would see large changes in range that you'd have to map to the topography. It would have been extraordinarily challenging. So how the optical navigation worked is we took as I mentioned, we mapped the asteroid in detail, and particularly the candidate sites and this Nightingale site are ultimately our site. We mapped in great detail. We derived features from the local topography and loaded those features onto the spacecraft. We allowed the spacecraft to do its own onboard navigation during the ultimate sample collection event. That means it was taking images of the surface, recognizing the features we had mapped, and then updating its position and velocity as it descended. Not only did it update its position and velocity, as you can see in this video. All these annotations are updates of positions and velocity, but it also made 2 maneuvers to descend to the surface. Those maneuvers were preloaded but adjusted on board the spacecraft based on its updated position. Okay, I mentioned the cars in the parking lot. Every red area or facet, as we called it in this animation, was hazardous terrain. So not only did we update the position and velocity, updated the maneuvers used to descend to the surface, we allowed the spacecraft to make a decision at 5 meters above the surface. And it made that decision based on its calculation of whether it was going to touch a hazardous facet or a safe facet. And if it had determined above a certain probability that we were going to touch a hazardous region, the spacecraft would have aborted that attempt at 5 meters. And as you'll see later, probably would have disturbed the surface wildly. Fortunately, we didn't. So we were successful on our first attempt. And this is what it looked like. Yet another surprise from our target asteroid. Well, we had lots of pre-launch testing of sample collection with various types of simulant representing the asteroid material. None of them were as energetic as this. This is on the left is the before image of what you see is the sample collection mechanism at the end of the extended robotic arm on OSIRIS-REx. On the left is the before, and on the right is what we call liberated material from the surface of asteroid. So you see how easy, right? This is a 500-meter object. It's a microgravity field. It doesn't take much to liberate a material from the surface of asteroid, and we liberated plenty of it. This is a camera, another view of it that gives you a better sense of the debris field that we created, right? So you see the spacecraft making contact, and then you just see lots of material being liberated, which is fantastic, right? Because what we knew was we had touched the surface, and we saw lots of different types of material fly by the spacecraft, including lots of fine-grained material, which wasn't evident in most of our sample collection, right? In the site selection was a lot of discussion about how much material was actually ingestible into our collection mechanism. So we were really excited to see all this fine-grained material fly by because we knew some of it must be in our collection mechanism. So after we had done the collection events in the days following, we had a plan to image the collection head and measure the mass by extending the arm and rotating the spacecraft. We did the first part, which was imaging the collection head, and this was what we found. So this, you can imagine, the collection head is out in front of the spacecraft body. We're looking at it, and what do we see? We see lots of fine-grained material emanating from the collection head. And a trained eye on this, who knows the anatomy of the collection head, can find there's some shadowing in here that indicates we had ingested some larger material too, and we had a flap that was meant to contain the collected material. That a large rock had wedged itself into this flap and was allowing material to escape. It was a lot like a salt shaker. Every time we moved the collection head, more material came out. So we abandoned the idea of moving the arm further, and we very quickly pivoted to stowing the collection head into what you see here is a sample return capsule. This is the only part of this. Did it actually show that? Sorry, I must have. Yeah, so this is the only part of the spacecraft that returned to Earth. We stowed our sample and got on our way back. Oh, by the way, one other challenge. We did all this in the middle of COVID. So you can see our celebration at the TAG event. And of course, right, we were in the depths of COVID in this period of time in 2020. But you know, we had a fantastic team, and we spent a lot of time with each other before the pandemic, which allowed us to build a culture of trust and good communication that saw us through the pandemic. This is our journey home. So we made a departure maneuver from the asteroid in May 2021, headed back to the Utah Test and Training Range for the sample return event itself. And you can see the journey back in terms of the orbit, the release of the capsule, and then it made its way through our atmosphere at high speed, hypersonic speeds. And so, of course, we had a large IR signature. Ultimately, our main chute deployed, and we coasted down as we had planned inside the Utah Test and Training Range, which you can see here. So we had about a 58 by 14 kilometer ellipse that we had projected our landing in. We landed safely in that area. I'll just show you some imagery from the spacecraft. This isn't a great, we didn't have favorable illumination on this. Sorry, it's a bit hard for me to see this, whether it's playing or not. Yeah, so this is a camera on board the spacecraft as we release the capsule from its way. So this was the spacecraft. This was the end of OSIRIS-REx for the spacecraft and the beginning of the Apophis Explorer. So we're on our way to near-Earth asteroid Apophis. This is what we saw from the ground. These are cameras, systems at the Utah Test and Training Range. Really hard for me to see. Yeah, this is playing. So these are two seminal moments in the entry, descent, and landing. We were all anxious to see the parachute deployed, and it did ultimately. And then see our capsule land again on the ground. Once we saw this go over the horizon from this point of view of the sensor and saw the parachute deflate, we knew our capsule was safely on the ground. And we were extraordinarily lucky. We actually landed within a few tens of feet from a road, which are few and far between on the Utah Test and Training Range. It actually made the recovery operations fairly easy. You know, practice all these contingency things didn't come to fruition. We recovered the sample, brought it back to the curation facility at Johnson, and discovered that we indeed had a sample that exceeded our expectations and our requirements. We finally measured the sample at 121 grams, and our requirement was 60. So we have more than twice as much sample as we had expected.
That's it.
There you go. Oh, here, turn it over to Dan.
I'll take next.
Oh, sorry.
I'll give the.
Yeah.
Okay, so I'll give the overview of our navigation from the sample collection to the Earth return. Let's see. Okay, in August of 2020, we had performed our last rehearsal, named the match point rehearsal. This rehearsal was exercising the 3 critical burns to get to the tag, or collect the sample. The orbit departure maneuver, the checkpoint maneuver, and then the match point maneuver. So after the rehearsal, the spacecraft had drifted away from the spacecraft, and then we performed a series of maneuvers to come back. And then you can see where we entered back into approximately a 1 kilometer orbit. It was actually smaller than that, 800 to 900 meters in radius. And this orbit had about a 22-hour orbital period. So to get to the correct departure point, right here is where we're going to depart orbit to put the spacecraft on a trajectory for the tag. We had to come up with precisely position the spacecraft at this point very accurately. And to do that, we performed a couple trim maneuvers to align the orbit plane to the correct plane. And then we performed a couple phasing maneuvers. So this is the trim maneuver, orbit, and then we phased with these where is it, P1 and P2 maneuvers, really small maneuvers to help phase, so that we met the conditions right there for orbit departure. The better we perform that, the better we would perform TAG. And then after the orbit departure maneuver performed in October of 2020, the spacecraft then flew autonomously. It navigated itself autonomously with the natural feature tracking algorithm that Rich had spoke about. And that algorithm had, let's go to the next slide. So this is showing an edge-on view of the spacecraft, or on the orbit. This is the orbit that we were in, and then here's where we departed. This is approximately a 4-hour overflight. And then once the orbit departure maneuver happened, like I said, the spacecraft autonomously navigated. It had to slew to obtain imagery of the asteroid, which were, these images were correlated with known landmarks. And then that, like Rich had mentioned, updated the spacecraft state, and then updated the timing of these the checkpoint maneuver and a match point maneuver. The checkpoint maneuver stopped the spacecraft forward motion and allowed these spacecraft to descend to the asteroid. And then the match point maneuver matched the rotation rate of the asteroid. So that's when the spacecraft touched down on the surface, there was no lateral motion, or minimized lateral motion. And then on the right is showing the sample site collection. The tag site, and I guess we called it Nightingale. The yellow circle represents the 50 or 25 meter radius pre-launch requirements, while the green shows what we're faced with after we got there. We couldn't find any places larger than 8 meters in diameter. And then the red shows the red ellipse shows the dispersions from the orbit departure maneuver, so that the red represents the possible areas that we could have tagged. And then this shows, so the left and the center one are showing our rehearsals. And the first one is a checkpoint rehearsal that we did where we exercised the orbit departure maneuver and then the checkpoint maneuver. And then we backed away about 60 meters from the surface. And then the middle plot shows the match point rehearsal, where we exercised all the maneuvers up to the match point maneuver. We performed the match point maneuver, and then backed away from the asteroid about 40 meters from the surface. As Rich had mentioned, the red areas and the yellow represent hazardous areas where the spacecraft would have, if it detected that we were coming down with its onboard algorithm, if it detected that we're coming down in those regions, that we would have backed away. But fortunately didn't. And then this on the right shows the actual tag where we tagged. The pink location is where we reconstructed where we ended up, right here. And so we were less than a meter from the target. And then after tag, the asteroid drifted away from the asteroid for about 5.5 months, and then we brought it back to observe the aftermath of the tag site to see what changed, and look at the scientists wanted to look at the dirt that had been exposed. We did that in April of 2021, and then about a month later, on May 10th, we performed the asteroid departure maneuver. This asteroid departure maneuver targeted us to a 10,000 kilometer flyby of Earth. We wanted to keep the spacecraft from impacting the Earth until the last maneuvers, when we were committed to do the entry for the sample release capsule. So we had a strategy to perform maneuvers with successfully perform maneuvers with with smaller and smaller dispersions, and so that we can bring the spacecraft closer to Earth until we were ready to for entry. So in about a let's see, I'm sorry. In the September of 22, we performed the TCM-9 maneuver, which took us to a 2,000 kilometer flyby. And then in July of last year, we performed the TCM-10, which brought us to a 200 kilometer flyby. And then finally in September, 2 weeks out from entry, we performed the TCM-11, and then a week later we performed the TCM-12 maneuver. Those are our final maneuvers to target entry. We were targeting entry with at a certain location on September 24th with a mean sea level at a mean sea level of about 133 kilometers. And then we had requirements to target a flight path angle of minus 8.2 degrees within plus or minus 0.08 degrees. So then about 4 hours out from entry, we released the sample release capsule. And then about 20 minutes later, we performed the divert burn, which diverted the spacecraft bus away from the Earth impact and placed it on the trajectory for going to Apophis in April of 2029. So this shows the little overview of the flight path of the spacecraft through the atmosphere. At the at the entry interface is where the dynamics of the governing the sample release capsule's motion change from astrodynamics to atmospheric dynamics. And then let's see. So when we entered, we were traveling or the spacecraft or the SRC capsule was traveling about 12.4 kilometers per second relative to the Earth atmosphere. And then then we went through peak heating, and then about about a minute later we had our peak deceleration. Then we were supposed to then the drogue chute was supposed to deploy, but we I don't know much to say about that, but it didn't. We saw that it didn't deploy, but then fortunately the main chute deployed about a few minutes from touchdown. And then when it touched down in Utah, it was about 14 minutes after entry into this from the entry to the atmosphere. This shows our final Earth targeting for the sample release capsule. So the we were targeting we had these requirements to target within 0.08 degrees for the flight entry flight path angle, and those are represented by those red lines. And then the yellow ellipse that's on here represents areas that were would have been fine, or I'm sorry, these were if the spacecraft was in that area, then we knew that was within allowable areas on the Utah test and training range. The red area is our what we our design ellipse, which was developed pre-launch. And then the green and the The little red ellipse represents the TCM-11 and TCM-12 targeting maneuvers. And then that black spot shows where we reconstructed where we ended up. And then, like Rich was showing, the landing ellipse in the Utah Test and Training Range. Here's that yellow ellipse is the allowable area that we could have landed. This was negotiated with the Utah Test and Training Range folks to make sure that we want to make sure that we didn't have a condition where if we're just on these weird areas, not our expected dispersions, and we didn't want a no-go to prevent us from landing the capsule. So we wanted to bump out the possible areas as much as possible for allow any contingencies that might happen. The dark red ellipse shows the design ellipse that I had mentioned before, was developed pre-launch. The lighter red ellipse shows the TCM-11 dispersions, and then the cyan ellipse shows the TCM-12 dispersions. And then superimposed on that is several daily orbit determination solutions that we performed. And then finally at the yellow is where we landed. And this was actually one of the solutions that we had been looking at with some experimental weather data that we didn't have in our nominal baseline plans. And so when we entered that data, we didn't want to depend on it, but it looked like that data might have been correct. And I believe that's it. So now we'll have Danny go for.
Okay, thanks, Pete.
Yeah.
I don't know how you all are feeling, but looking at these last two talks, it's just incredible that this happened. I mean, how many things had to go right, the planning, the work. And I just want to thank everybody involved in everybody involved in OSIRIS-REx for making this dream happen. You made a lot of sample scientists and future scientists happy. Okay, so you're going to hear a lot about the science of OSIRIS-REx from Dante in the next talk, so I'm not going to spend a lot of time on that, but I do want to emphasize just the importance of sample return, specifically for understanding our own origins. And it's probably no secret here, OSIRIS-REx, the first letter O stands for origins. So a lot of our science and the hypotheses we will be testing really have to do with understanding how life started on Earth, the only example of life we have, and the possibility that it could extend elsewhere throughout our solar system. And we heard David talk about the Stanley Miller experiment, which was a great experiment, showed that you could produce the building blocks, in the early Earth's atmosphere from lightning and other sources, called the homegrown synthesis hypothesis. With OSIRIS-REx, we want to test an alternate theory, and that's that asteroids like Bennu and comets could have seeded the Earth with the chemical ingredients for life. Roughly 4 to 3.5 billion years ago, when we think life first took hold here. And here's the challenge, and it's kind of counterintuitive. You'd think, hey, if we're going to try to learn how life started on Earth, we'd look at Earth rocks, right? The evidence should be here. Well, that's actually not the case. The oldest rocks on Earth have been heavily modified by plate tectonics. Earth's great recycling program, heated and under pressure, and it has basically destroyed the evidence of the prebiotic chemistry that we think led to life on Earth. And so we need to go elsewhere. We have to go to primitive asteroids and comets to try to understand what that prebiotic chemistry looked like 4.5 billion years ago, right, prior to the origin of life on Earth. And then I'll be tying this into Mars as well. Mars is another unique place, right? It's different than the Earth. It hasn't experienced the extensive plate tectonic activity. So we've got, 4 billion-year-old sediments on Mars, actually waiting to be brought home, which I'll talk about here in a second. So we can learn about that period when life started on Earth on another planet in a similar environment, a similarly habitable environment. So that's just pretty exciting. And again, we can't learn these things with the rocks on Earth. We have to go to these places. And you see in this picture, the tag SAM shortly after the 2 bolts that had cold welded were removed, revealing the entire sample collection, 121.6 grams. So it doesn't really look like much, but let me tell you, this is a lot of sample. Okay, this is going to last for generations. There are folks on our team that actually take 100 micron dust particles. You can barely see with their eye, and they make sections out of that. We just sent some to Berkeley, and I was 300 micron grains, and he was like, "This could last forever." I mean, just that. So this, twice the requirement, and this is going to be around forever. It's just really exciting. This sample, of course, is not here. Otherwise, I'd probably be arrested right now. It's at the Johnson Space Center in a specially designed curation lab. So, these are pristine samples, right? Have never seen the Earth's exposure in contrast to meteorites. So we want to keep them that way, right? We don't want the science evidence to be tainted. So these nitrogen glove boxes were designed to keep these samples under nitrogen. And these samples are already moving around the world. Over 200 scientists will be studying these. We actually just got a sample yesterday at Goddard. I'm really excited to get back to the lab and look at those. We've got over 65 techniques now that are planned as part of our sample analysis plan. Many more will be used in the future, guaranteed, some that haven't even been invented yet. But the one at the bottom there, the synchrotron facility there at UC Berkeley, that's I was talking about those 100 micron grains that they're analyzing. To do that, you need instruments that are the size of buildings, right? You simply can't fly these. So this is why we do this. And then, of course, we can't forget about the next generation. So most of the sample, over 70%, what you see in this bottle, will be archived for future generations, which is pretty special. I know Jamie Elsel is here. She's been looking at some of the lunar samples that were sealed from the Apollo missions, over 50 years later, right, using techniques that weren't invented then. And Jamie wasn't even born then when that happened. So again, this just really shows you the value of sample return. And I just wanted to show this picture. This was a really exciting day. This was the first sample that we got at the Astrobiology Analytical Lab at Goddard. We're pointing to it. It was actually stored in this container under nitrogen. And then you see it there in the upper left between the 2 glass slides. So that was, I think, 52 milligrams of material. And just to kind of impress upon you how little is required to get some pretty amazing science, we took 1 milligram of that. 52 milligrams. That's less than 0.0008% of the return sample. We pyrolyzed it using pyrolysis gas chromatography, mass spectrometry. Angel Moharo there on the left was the one who had the privilege and exciting day of doing that. And boom, we, just from that small sample, we're detecting the chemical building blocks of life, which is pretty exciting and one of the main objectives of the mission. So we're just scratching the surface here. We've got a lot more work to do. But man, it's been a really exciting start, and we returned the right material. We went to the right asteroid. There's no question about it. This is an astrobiologist dream. Okay, so I'm going to turn to Mars. The other half of my job is thinking about Mars and how we get these Mars samples back. But really, my career in astrobiology started, and David talked about Allen Hills 8401, known as the Mars rock. This potato-sized Mars meteorite that was blown off the surface and discovered in Antarctica, and really got a lot of the community excited. At the time, I was just finished my physics degree, UCSD. Thought I wanted to study black holes, believe it or not, and get into astrophysics, but this changed everything for me. Actually went back to school, studied organic chemistry, and just the idea that life and the building blocks could be transported between the planets, like swapping spit, was just, it was fascinating. And so I got into this field. And of course, we're still debating this evidence. Is it Martian? Is it terrestrial? And of course, one of the challenges here is that all meteorites are contaminated, right? As soon as they hit the Earth, they're contaminated, which is why it's so important we get these pristine materials. And Allen Hills was no exception. But I want to emphasize that, that worm-like structure there and the magnetite grains, these were made using, electron microscopy techniques that we can't fly. right? And by using these powerful techniques, we're able to even pose the question of the possibility of life, which we wouldn't be able to do with in situ measurements. So I want to really emphasize that point again, the power of lab technology and being able to ask questions that you wouldn't be able to otherwise. Okay, and I know Jim showed this picture of the Curiosity rover, the SAM instrument there, which was built, integrated, and tested at Goddard. Paul Mahaffey, original PI, Charles Molespin took over. This has been an incredible instrument, over 12 years working, functioning on the surface of Mars. And really, this provided the first unambiguous evidence for Mars organics. And there was a lot of debate about whether there'd be any organic carbon. After Viking kind of had the null result, Mars doesn't have a magnetic field, so it's constantly bombarded with radiation, which can destroy organic molecules. And so we weren't sure if we were going to find preserved organics, but boom, we did, including these long chain hydrocarbons that we think might be products of like fatty acid cell wall material. But bottom line is we don't have the technology on that rover to definitively show whether or not that organic matter is from biology or not. And so we got to bring this stuff back. And we started that with the Mars Perseverance rover, currently exploring Jezero Crater, another lake environment, a long-lived lake environment we think was habitable. You can see the evidence, it's clear with that delta. There was a river flowing into a lake depositing these sediments, sedimentary rocks, which again are ideal, the types of rocks that you want to bring back to look for evidence of life. Allen Hills 8401 was, a great start, but it's an igneous rock, right? It's a volcanic rock. These are non-ideal to search for biosignatures. These materials are the ones we want. And you see here the Perseverance Rosa actually collecting cores, about 6 centimeter, kind of the size of a pencil. This is a model of one of the tubes. And actually I think it's 24. Probably shouldn't say that, but 24 samples have now been collected. 10 of them you see out there were actually placed on the ground at a place called Three Forks, kind of as the first depot. It was more of a contingency plan in case something happened to the rover. We'd have samples on the ground to pick up. The duplicates of those, so we collected them in pairs, are currently on the rover, and we continue to collect more and more samples in the rover that will hopefully be returned to Earth. Up to 30 of these is the plan to bring back to Earth. And just to emphasize, again, why this is so important. So I talked about, most of the Mars meteorites are volcanic rocks. Again, not the ideal samples to look for signs of life. We've got sedimentary rocks with Perseverance, and these are the ideal ones. So bring them back. We can do the things with these samples that you just can't do in situ. We can make thin sections, shown on the left there, to understand the mineralogy and petrology in great detail. We can do wet chemistry to look for some of the building blocks in ways that aren't possible. So it's just that the extraction methods are more advanced here on Earth. And then of course we've got, an unlimited number of instruments to really figure out whether or not those organics and other chemicals are from life. And then I just want to finish off, I know we're short on time, but we've talked a little bit about the science benefits of Mars sample return, but really for me, it's the one on the right there, the inspiration. I don't think we can underestimate the value of these missions for just exciting the next generation. There will be many, many people who get into planetary science, get into astrobiology just because of this Mars sample return mission. And I think that's it.
All right, so I'm very happy to be here on behalf of Brett Denevi and the entire Artemis 3 geology team to talk about what we're planning on doing for sample return in the Artemis 3 mission, and also talk a little bit about going beyond that. Danny talked about the value of samples, and I can't emphasize enough how much more science we can do with those samples back in our labs. I want to emphasize here, though, that when you have humans enabling the sample return, it really brings it up so many more levels. We've got 180 grams of sample there from OSIRIS-REx. From the Apollo missions, we brought back 381 kilograms. So that's 3 orders of magnitude more samples that we were able to bring back just because of the scale of the missions. So, you know, with those samples, you can retain them for decades and decades and decades and have those available to learn from for generations. And then the other benefit of having a crew there collecting the samples is that you get a lot more of the geologic context compared to a meteorite where you have no idea exactly where it came from. You know about what this rock that you picked up on a crater rim, which crater it came from, and you know, its relationship to the local geology. And you know, spending time training the crew so that they can use their you know, their experience and their knowledge of the science to help them high grade those samples. So not only are we getting 3 orders of magnitude samples back, oh, I don't know how I did that, but it's also high graded samples because you have these astronauts in the loop who are helping to pick out the right samples to bring back. So Artemis 3 mission is a complicated endeavor. There are many, many steps involved in this, and there's a lot of demonstrations that we are accomplishing through this mission. So there's a lot of technology that we need to demonstrate and a lot of objectives related to that. The surface element is just that one little part there. Step 12 here is the surface element where we're going to be on the ground and collecting those samples for return. And so I just want to stress that the mission is going to accomplish a lot of firsts, and collecting these samples is a very, very important part of the mission, but it's not the only thing that Artemis 3 is going to do. But that said, these samples are going to provide transformative science. We are going to learn so much about the moon from the Artemis mission, Artemis 3 mission. So part of why we're going to learn a lot after we already have all these Apollo samples back here on Earth is that Artemis 3 is going to a very different region of the moon. You know, this map on the left is showing where we got our Apollo samples from the near side, mid to low latitudes, a lot from the Mare regions of the moon, whereas the map on the right is showing, it's tilted up a little bit. You're looking at the bottom there, that's the South Polar region, and the candidate landing sites for the Artemis 3 missions are all clustered there. In that South Polar region. It's a very different composition of the moon. It's the highlands, and it's also a much different space environment because it's in the polar regions where the temperatures are different, the lighting and the interactions with the space environment are different. So we have a lot to learn just from this new location that we're going to visit. So the geology team has come up with 4 science goals for geology with Artemis 3. Those goals are to understand the early evolution of the moon as a model for rocky planets, to determine the lunar record of inner solar system impact history, to explore the regolith in the unique circumpolar region as a keystone for understanding surface modification processes on airless bodies, and then to reveal the age, origin, and evolution of a solar system's volatiles. And that last one is my particular area, so I'm just gonna dive into that one real quick and talk about what we hope to do there. In the South Polar region, there are regions of permanent shadow where the temperature is very cold, and there are water and other volatiles presumably trapped in these regions. And so these permanently shadowed regions have ranges of sizes, big and small. From Artemis 3, we expect that we should be able to get into some of these smaller permanently shadowed regions and collect samples there. And they will help us understand being able to analyze these back on Earth. We should be able to understand the origin of these volatiles and the abundance. We also want to understand if there are processes going on that are actively transporting volatiles to these permanently shadowed regions on a continual basis. So we're going to be doing some studies to assess that. And then very interestingly, we can use the fact that landing the Artemis mission on the surface moon is an active volatiles experiment, because as the lander is coming down, it is depositing exhaust from the plume onto the surface. And so we can use that as an experiment to understand how volatiles interact with the surface and learn a lot there. So on Artemis 3, there are going to be 2 crew members on the surface for about 6.5 days. We're going to have a variety of tools for them to work with and collect the samples. They're also going to have cameras to characterize the areas and the samples. And we expect 100 kilograms of return mass, and that includes both the sample and the containers that will be holding those samples. So that's a very quick snapshot of Artemis 3. As we're looking down the road to future Artemis missions, we're going to have handheld instrumentation that can help even further high grade the samples that will come back. We hope to be able to bring back cryogenic samples so that we can understand the volatiles in their frozen form. There'll be expanded mobility with the Lunar Terrain Vehicle. And even as Danny was talking about returning those samples from Mars, there's an idea in the Planetary and Astrobiology Decadal survey about the Endurance A mission, where a rover would collect a bunch of samples from the South Pole Aiken area of the moon and leave those for astronauts to return. So that could really expand the effective area that we can return samples from. And then as we build up an Artemis base camp, there's a lot of complex field investigations that can be conducted. So the future for lunar sample return is really bright. We're very excited about it. And come with us to the moon.
Okay, thank you, Dana. We only have a few minutes, but I'll take a few questions from the crowd. Over here.
Down here, window.
Yeah.
And then we got one in the back right next.
Right back there.
So that one first.
Yeah, go ahead.
Hi. I noticed that the last 2 asteroid material missions have been just surface samples. I was curious if there's any scientific benefit in maybe drilling deeper into asteroids, and if that's some technological thinking that's been done.
Yeah, there actually have been missions to look at that. I think it was called the ARM mission at one point. We're actually going to pull a near-Earth asteroid into cislunar space and then have astronauts go there and core. And yeah, the scientists were getting really excited about that. You get information with depth. These asteroids are also exposed to cosmic radiation, right? That could damage some of the organics, so the deeper you get, potentially the better. So yeah, I think there are some science drivers for that. It's hard. It's really hard. We learned that with OREX. These things are not behaving like we thought, right? We almost plunged all the way in. So it could be challenging to do that.
There's a couple other things. The non-cohesive nature of Bennu, why so many particles emanated from the surface, is because it was loosely held together. So our estimate is our sample collection mechanism actually penetrated Bennu by a half a meter. So we were inside the subsurface of Bennu. Also notable, right, that the JAXA mission Hayabusa 2, they actually they had a explosive that they deployed to the surface of their target asteroid Ryugu, and then they collected a sample of that exposed regolith.
Okay, we'll take the question from the back.
The tubes that were dropped by the Perseverance rover with the samples, do those have any trackers in them in case they get blown away by the Martian winds?
Yeah, so they actually, well, they don't have any sensors on them, if that's what you're asking. But they've done some modeling, looking at dust accumulation, and it shouldn't be an issue. They won't get buried in the location that they were placed. But yeah, that was a discussion at one point. We were worried about that. Can we find them? But no, that won't be an issue.
Okay, for our final question.
Hey, here. The Bennu sample, has it been fairly homogeneous across the sample, or do you see variations between the particles?
Not homogeneous. Lots of variation, and we're XCT. Dante will probably show one of the XCT scans, but oh my God, even at the centimeter, sub-centimeter scale, there's all sorts of globules and voids and lots going on. Yeah.
That concludes our panel. Thank you very much.